All right, I'm going to go ahead and get started. I know there's folks still filtering in, and there's also me standing just eating lunch. So I'm going to try to keep this relatively simple and informal. This morning is a kind of potpourri of additional topics, so I'll be continuing with RL tomorrow. But today, one thing that I thought I could do, so you've seen a lot of Gaussian processes, I guess. So I wanted to talk about the counterpart in the discrete world. So Gaussian processes are very flexible ways of modeling continuous functions, right? What's the discrete analog of that? And next week you're going to be hearing more about some pretty cool Bayesian non-parametric models about the Dirichlet processes and the Doshi processes. And these models all come from Poisson processes. So what I thought might be kind of fun, because we have this additional block of time, might be to just give you an intuition of what Poisson processes are. And the goal here, again, I'm going to keep it pretty light and conceptual, but I'm hoping that now that you have the mental picture by the end of this hour, that you can go to, for example, Kingman's book, Poisson Processes, kind of classic book in this area, or you can go to Antoniak, Blackwell, McQueen, all these like old papers on the Dirichlet processes, Ferguson, or you can go to the newer stuff and understand, again, you have the mental picture.
And then they have like so many regulations, so we get like 700 sensors or something.
So before I talk about Poisson processes, the first thing that I want to put up is the Poisson distribution, which I'm sure everyone here is familiar with. Right, so Poisson distribution is a count-specific distribution. There's your equation. X is discrete. And so you end up with something that looks like this, right? So this is the number of counts, 0, 1, 2, 3. So it's telling you the number of counts that you're going to see, right, in a particular drop. And importantly, there's no upper bound, right? This tail goes off to infinity, but you're never going to really get it and get an infinitely large value, right? The value that you get is always going to be bounded. And there's always a mean. So the mean of this distribution is lambda, which you're going to call the rate parameter. And just as a review to put it on there. So something that folks may or may not know is that the Poisson distribution comes as a limiting distribution of a binomial distribution. So what's a binomial distribution? Let's review. There's many exciting things about Poisson distributions. I'm just telling you the key facts that are necessary or relevant as we start to build that process. The binomial distribution also gives us a count. So this is going to count the number of, let's say, counts number of heads in n flips. If the flips are IID and there's some probability P of success. Right. And if you look at the binomial distribution, if you think about what is the expected number of heads that you're going to get, right? The expected number of heads is very simple. We have n flips, they're all independent from each other. And each flip has a probability P of success. So the expected number of successes in one flip is just P. And the expected number of successes in n flips is just n times. So as it turns out, if you keep this thing constant, so you want to keep the expected number, so this is just the mean of the distribution, right? You want to keep the expected number of heads constant, but you increase n out to infinity, so now you consider an infinite number of flips. That limiting distribution will give you this Poisson process. So let me just say that one more time, because if you haven't heard it before, it's a kind of funny idea. So the idea is that we're going to try to increase n, right? So when we increase n, p is going to decrease. right? Because we want n times p to stay the same. We want the number of successes to stay the same. So we want this thing essentially to be equal to lambda from up here. So we want this thing to stay the same. And if we work out all of the math of the limits, which I'm not going to do for you right now, what you will find is that you'll end up with this as your distribution. So this is your distribution. If you have an infinite number of coin flips, how many heads will you get if the average number of heads is given by this one? Okay. So I just wanted to store that piece away, this idea of the Poisson process as a limiting distribution from the binomial, because we're going to come back to that in just a few minutes. So now I'm going to show you a very, very different picture of what a Poisson process looks like. It's not going to look anything like that distribution before, but it'll in just a little while. So let's say that I have some space, right? And if I have some space, what sort of process could I put on this space, right? Well, you talked about Gaussian processes, right, over several lectures. So you could imagine that there's some continuous distribution that's fixed over this space. That's one thing you could have, right? That every location has, for example, a temperature or some other, humidity or whatever associated with it, and that's sort of smoothly varying. But there's other things that aren't necessarily well modeled by this sort of continuous thing. So for example, if you're looking at stars in the sky or trees in a forest, you might have, your data might look like dots, right? You might have points as the thing that you're observing. Okay, so it's not some continuous thing, but there's a star here, there's a star here, there's a star there. So then here's where we get to this discrete analog, I guess, or the kind of core discrete distribution. We're building up a lot of machinery in Bayesian non-parametrics on the discrete side. Is that we are interested in this sort of, like modeling this sort of thing. So this is called a point process. And here I've written it in 2D, but an area where it was initially studied quite a bit was in queuing theory. So you imagine now that you have an axis that's time, right? And you're looking at, when are arrivals coming in and how are they being processed? So this can be relevant for all sorts of logistics types of things, like routing buses, routing over the internet, all sorts of applications where you have things that are arriving and you have to process them in some way, right? So that's another example of a point process, where now each of these x's here indicates an arrival of something, or a departure of something, or something, right? And again, this is a very different type of object than putting some sort of function, because now these things are coming in at discrete times, and then you have to process them. Right? Another version where this corresponds to time, if you look at firings of neurons, you again have this situation where neurons are firing, they fire at a relatively discrete, they might have a potential, but they're still firing at a discrete point in time, right? So again, this is a notion of how do we model these sort of discrete things that are coming in. And the Poisson process, as it's going to turn out, is the very, very simplest version of this. Again, just like how the Gaussian is one of the simplest distributions you can get, the natural limiting distribution of a variety of things, the Poisson process, coming from the Poisson distribution, is really the simplest thing you can do to model this sort of data. So what do I mean by simplest, right? So let's talk about what that means and unpack that a little bit. Let's go back to this picture over here. Now in this picture I put down some x's, and let's say that I create this somewhat artificial, perhaps, desiderata, and I say that in terms of simplicity, I want to lay down this one criterion, that if I put down some block over here and some disjoint block over here, so let's call this A1 and A2, then the number of things that I see in A1, the number of points in A1, is independent from the number of points in A2. So what this is saying is there's something about locality going on here, right? that this process is not being affected by things far away. That if you're in this block over here, then only that block matters for the number of things that you see inside. This is a very key assumption, right? And it's not true in a lot of cases. In a lot of cases, you might expect to see other forms of correlation, right? You might expect to see, for example, repulsion, where if you have a tree here, maybe you don't expect to see a tree right next to it, right? But I could imagine creating two boxes like this and like this. And what I'm saying with this assumption, or this criterion, is that I can put any two boxes, as long as they overlap, I'm going to require that the number of elements inside this box, the first one and the second one, are independent of each other. So again, I want to point out kind of the limitations of this as we go through, but this is the simplest sort of model, or one of the simplest models you can imagine, right? Where every version of blocks that I can put down, as long as they're not connected with each other, have to be independent. So that's a very strong criterion, and that's the criterion that leads us to this Poisson process. We essentially need no other criterion. That if we have a process where this is true, we're going to end up with something that's a Poisson process. So why is it called a Poisson process? Well, what we will have is that in each of these blocks, the number of points in each block will be Poisson something which we're going to fill in over the course of the lecture. And again, this is going to be a consequence of the fact that we're requiring disjoint blocks to be completely independent of each other, or with very small additional assumptions that we're going to do. So one thing that I want to do very briefly is just lay out what we need to do in terms of things being a probability space and making this formal. If you haven't seen any measure theory, that's fine. If you have, this will be very simple. Again, my goal is that you will have kind of the images or pictures in mind, so if you try to read one of these more complicated papers, you're able to kind of link to these core ideas and you know what they're referring to. So how do we define a probability space? And this is general. I'm just going to start us there. So we need three objects. And the first object is a set of outcomes. All the possible things that can occur. So right now we haven't connected it to this picture. We will in just a few moments. Then we need all subsets of those outcomes, or some set of subsets of those outcomes. Yeah, I'm being pretty loose here. And then we have, this is our probability measure, gives us the probability of each subset. So for example, in this case, our omega corresponds to this region, right? In our region, we can have points, right? So that's the starting point. And what are the subsets that we can draw? Well, those are the x's. So this is our region. These are our collection of points. I'm going to the kind of standard, just big pi. I'll draw it big and see if that's a capital. So this is our collection of points. So these are our x's. So when I draw pi, I mean the collection of dots, right? So that's a subset of this space, omega. And then what we need to do is we need to define what's the probability of any collection of these points. right? So formally, that's how we're setting this up, right? Connecting it to the measure theoretic notation. And I'm doing this mostly because if you see this in the paper, you can say, oh, right, I kind of know what that's talking about. It's actually not that complicated. When they talk about these subsets and sigma fields, in our case, we're just talking about points that are. All right. So now let me put down a little bit of notation. So I'm going to write n of a as the count of the number of the, so now this is the particular set of points, right? Intersected with a region A. Actually, let me keep this picture up because it's really important. So here's our region A. There's some points inside. There's some points outside. And n of a is just the number of points inside this region. And this notation is saying, right, this is a collection of dots, right? It's a collection of points. And where does that collection of points, that subset, intersect this space? Okay, so it's just going to flip out. So a Poisson process needs two things. It needs to have the disjoint A1 through however many A3. So if disjoint and n of A1 are independent of each other. And also that the number of points in A is distributed with this Poisson distribution, which has to do with this mu of A, which I'm about to define. So this is the measure. So mu is a measure. And what this is saying is that this is roughly saying the size of A, right? Like how much mass is inside A. So right now I've just drawn this as a flat space, right? But we can imagine situations where I have this idea that there's certain parts of this region, maybe that if I'm modeling trees, here are places with more water. So I think that these areas are generally more likely to have trees. And maybe these areas are less likely to have trees, right? Something like this. And so this is what I mean by this measure mu. That even though we're looking over this space and we're requiring that each of the sets be disjoint, that isn't the same thing as saying that any patch of the same size needs to have the same probability, right? Key difference there. So if I have a box in this area which has maybe a lot of water and fertile soil, maybe we're likely to see more vegetation or growth or whatever, and this patch up here maybe has less. And that's what this mu of A term is saying. That let's look at the space, and so a very simple measure, say the best measure, would just be look at the size of the space, right? That's always valid. But you could have the other things as well, right? As the size of it, to measure roughly the size of the space. Yeah.
I don't really understand what it means for them to be disjoint, independent from each other. So what is the opposite case for two disjoint?
If they're not independent? What would happen? Like, can I give you an example? Are you asking for an example?
Exactly. Two disjoint regions.
No, for sure. Right. So for example, this can happen all the time. Actually, the trees example is a good one because it isn't the case that if I draw, like that picture I drew earlier, where if I draw two things very close to each other, and I can make them really tiny, and it still has to hold. So let's say I have this here, and I have something next door to it. Then in real life, I might think that things are kind of spread out, right? And sometimes it needs to be that case because, like trees, next to a tall tree, you won't have another tall tree, right? So if I have a tree here, then it's not independent. Like the probability of tree here is not independent. right? And then I can flip it around, we can think about mushrooms, right? Where like mushrooms always are clumping together, they grow in clumps. So here, if I see a mushroom here, I'm more likely to see a mushroom next door.
Okay.
And so with the Poisson process, we can't do any of that.
Okay, so does that condition ever hold? Is there a case?
Oh, are you, I see. So are you saying, is it ever the case where this assumption is reasonable?
Okay, yeah.
Yeah? So I think there's two answers to this question. The first answer is that just how we use Gaussian distributions all over the place and Gaussian processes all over the place because they're easy to use, right? Poisson processes are often used because they are easy. And in machine learning, you are always going to be butting up against this question of efficient inference and model mismatch. So there's situations in which maybe you have a more complicated model that better represents what's going on with your data, but you can't really solve it, and if you can't solve it, you still get crap predictions out. Versus you might have a model that's not very good for your data, isn't perfectly fit to your data, but it's good enough, right? But if you can do, because if you can do very efficient inference, you might actually get better predictions from the misspecified model, right? So that's answer number one, right? Same as why we use Gaussians all over the place, right? Because the ease of computation. The second reason why we are interested in these sort of things is that right now, I mean, I'm trying to make it concrete. I'm talking about trees and mushrooms and physical entities, right? But one of the big uses of this, which you will see next week, is for constructing these Bayesian non-parametric models. And now these point processes, these points are in a much more abstract space, right? Or they're in the linked variable space. So these points might represent topics, for example, that appear in a data set. They might represent means for like a mixture distribution or something like that. And then it might become much more reasonable to say, well, we actually don't have a particularly good prior on where these things should be located or how these things should be spread out anyway, so let's use a simple one. And because it's already one step removed from the data, the model mismatch is less big a deal. Right? And that's not to say that people haven't spent a lot of work on models that try to model that latent space more intelligently. But again, like as soon as you start, the more you're removed from the data, the more these things kind of become okay in terms of practicality. And then in terms of the math, you can just prove so many beautiful things that this is the one set of things where you can actually make a lot of things about. Any other questions? Yep. All right. Cool. And just one side note that I want to make is that if we have two regions like this that are intersecting each other, so if we had A1 and A1 and A2, what this implies is that we can always break this up and say that that this region here is independent of this region here is independent of this region here. So if we have overlapping regions, we can still compute the correlation, the covariance between those, the number of points in those regions. I'm not going to write out the math for that, but it's still possible to do. All right. So one question I want us to think about is what could these mean? Are there any limitations on what this mu can be?
So a question about the mushroom example, but also mu. So can we, for example, by mu having like very high density at some points and then like low density at other points, doesn't that induce some kind of correlations that suddenly nearby?
Well, that if you see a point here, you're also, so right. So an important point is that it's conditioned on mu. Everything is independent. So if I have a high density region here, then yes, like I can block it off into tiny blocks and probably I'll see points in all of them, right? But it's just like saying if you have a coin that's likely to come up heads, are the heads correlated with each other, right? So even if I have 0.9 probability of heads, every coin flip is still independent. So the same idea here, that each of these is still going to be an independent drop, even though you're likely to see a long flag. So in terms of limitations on mu, one of the key things that I've drawn this as is as a point process, right? So we don't have points on top of each other, right? Our set of outcomes is that every point, every location either has a point or it doesn't have a point, right? But we don't want them to stack on top of each other. So when we create the measure, that's one of our key considerations, or what is that we don't want it to be possible for basically a location, like a little zero measured blip, or sorry, a little blip should have zero measure. No. So how do we do that? The key limitation is that mu must be non-atomic. Because if mu had an atom in there, and that meant that, so what I mean by atom is like, if this was, so now I'm going to draw mu. So the point process has points, right? But mu is this, smoothly varying thing. If mu had an x in it, right, that would be an atom in mu, or a spot. Then suddenly I could have more than one point on top of each other. I could stack points on top. And we can show that very easily. So what's the probability that n at a particular location x is greater than or equal to 2? Well, that's just going to be 1 minus the probability that there's no points on that one point x, right? So now x is just a specific location, right? A single dot. So that's going to be 1 to the e to the negative probability of 0. Let's write it as m. Let's say m is the size of that atom that the measure puts there. Minus m e to the negative m. That's problem 0, problem 1. And this is greater than 0, and so that's a problem, right? So if any particular location had some finite probability mass associated with it, that's going to allow us to create situations in which the points, the x's stack on top of each other. So that's our limitation, that we want to make sure that mu doesn't have any atoms in it. Now, one way that mu is often constructed, here's the, mu must be non-atomic, is to think about something. So this is sufficient but not necessary for mu. Is to think about the rate function rather. So instead of thinking of mu of any particular subset, so mu is giving you the measure for any subset, right? So mu takes in a set, right? So mu took in, for example, mu of A. A is a set because A is a region. So the measure is giving you, taking in a set and giving you the size of the region, right? What if we had now a value associated, so actually this is a little sloppy. So each subset would have a mu associated with it. So let's consider now each location x as having some sort of rate. And find mu of A as the integral of that rate. Okay, so that gives us a way of saying, like, what's the size of any subset. So again, this is not a necessary condition, but it's a sufficient one. So here's like one way to create the mu's, and you just have to, again, make sure that you don't end up with atoms here. So what is this kind of saying, right? Like, I want to pull this back to our quote picture. Like, let's go back to the thing I started with the Poisson coming as a limit of the binomial. Okay, so all of this stuff, if we have this space, omega, right? Now imagine that I chop this space up into really tiny segments. Or first, maybe I start with the space of this sort of discretization, right? And then each one of these spaces will have a mu associated with it, right? And we can flip some coin, or sorry, not flip a coin, but flip our random number generator through, and we get a number for each one of these, right? Always possibilities, right? We just cut up our space. Now, what the Poisson process is saying, or where this comes up, right, is let's say that I change the discretization of the space, and so now I change it to be cut up like this, with many more finer grained things. Or maybe I just slice it in a completely different way. I don't want the distribution of points, the total counts in the space to change, just because I decided to slice it differently. Right? Like if I think that there are certain patterns of x's that are going to occur, how I slice this space should not change this pattern, right? It shouldn't be that if I slice it one way, oh, the x's look like this, and if I slice it the other way, the x's will look like that. Because you can think of the slicing as something that happens afterwards, right? After the trees have grown in the forest, I come in as the surveyor and I draw some boundaries. Should the boundaries change where the trees are? No, clearly, right? So that's a desired condition here. So another way of thinking about that is saying that the number of points in a particular region should not change, right? So this is like saying that expected number of heads that we talked about at the very beginning should not change. So let's say there's an expected number of points in this region. So let's say there's like an expected n of omega. So the expected number of points in the region should not change if I cut the region and say that actually I'm going to add up the number of points here, and then I'm going to add up the number of points here, and here, and here, right? That should give me the same total sum as if I chose this one, and this one, right? Kind of seems intuitive, right? Again, but this is a very strong condition. If you want it to be the case, then now you can sample in each region independently, right? That's kind of an implication. So in terms of comparing this to the binomial, what we see happening, if we imagine that I cut this into tinier and tinier segments, each one of these segments, when it becomes very small, you could think about, well, it's so small, it's probably going to have either 0 or maybe 1, right? The probability of having an x in a very, very small dot is getting very small, right? Because the space of that dot is very, very tiny. But altogether, we still want a certain expected number of points. So this is the same thing where we said from the binomial distribution, we said we want the number of heads to stay constant as the number of flips goes to infinity. And that seemed kind of weird at the time, right? When would you have infinite flips? Well, here is an example where you can't have infinite flips, because as I make these regions very, very small, you could imagine that now I have an infinite number of regions, and each one of those tiny regions is doing a little flip to decide whether or not it has an x. Right? And so that's how we end up with this Poisson distribution, this Poisson process. Because now any collection of these will have a certain number of expected. I'm going to pause for just a second. Any questions there? If you understand that part, then you can read all the other papers. This is really the key kind of notion about Poisson processes, or at least one of the key notions. All right. So if there are no questions, I'm going to talk now a couple of properties about these processes. This is a key picture to have in mind, right, when you think about these. Three or maybe 4 key properties of Poisson processes that are very useful. And these all have analogs, largely all have analogs in the Poisson distributions as well. So the first one is superposition. And that's to say that so first of all, the probability, if you have two independent Poisson processes, and we look at how they intersect in any region, they're basically never going to intersect with probability 1. Again, kind of makes sense that if we're putting down points in space and somebody else is also putting down points in space, the probability that 2 points intersect, unless there was like an atomic measure, right, that allowed 2 things to be on top of each other, or there was correlation, going to be 0. And so you're never going to have the processes intersect. And that's an important lemma to be able to show. Again, I'm not giving you any of the proofs, they're all in Kingman. But that's important to be able to show that the union of these things, I1 union I2, is a Poisson process with rate lambda 1 plus lambda 2. So this is the same thing as saying if you add 2 Poisson distributions, you get a new Poisson distribution, right? It comes from the same, or it's not the same thing, but it's coming from the same set of ideas. And remember, these are functions of x. So I can have one rate or intensity, and I can have another intensity. And that also means that we can slice it. So if we have a particular intensity, we can slice it into multiple things. So if I'm given lambda, if lambda x is given, we can split it into lambda x equals lambda 1x plus lambda 2x. And if for whatever reason we wanted to sample now pi 1 from here and pi 2 from here, we could put those points together to get a sample from here. Right? So you can imagine this is 2 different processes, we're putting it together, we get a new process, or we have an existing process that we want to cut up. And then each one of those little processes gets to take responsibility for some of the things that are created. So another important property is this notion of mapping. So if there's a mapping F from some S space into some T space, which creates no atoms, then F of pi, which is now a new set of points. So imagine there's some space S, we have points there, and now we have a new space T, and we take each point and we map it over according to this function F, right? And so maybe they end up looking like this. It's also a Poisson process. So there are a couple of logical things that this transformation can be that are kind of useful. So here's specific versions. We can stretch and squeeze. Again, as long as we don't, I'll show you an example that doesn't work. But as long as we're kind of careful and we don't mush things together too much or stretch things out too much, we can stretch and squeeze. So we can take this space and we could just stretch out certain coordinates or smush certain coordinates. And that's how you can take any Poisson process that has some interesting intensity or rate function and convert it into something that's flat. So you can take a homogeneous process. So this one could be lambda is just using some constant and convert it into any other lambda of x, for example. So you can always take a homogeneous process and make it into something homogeneous. So and again, like kind of in terms of thinking about what's going on, you can stretch and smush that measure around, or that intensity around. Another thing you can do is remove dimensions. Kind of common applications. So if you have the process that looks like this, you can take them and map them onto just one dimension. And this new thing is also going to be a process with them. So this is kind of interesting because an infinite number of things got mapped onto one thing, right? And that's still okay. And the reason that's still okay is that, again, for this 2D to 1D example, when you have a line here, that still has 0 measure. And so the probability that you would end up with 2 x's in the 2D space that are exactly the same, overloading now x, the same x coordinate is 0. So you're not going to have things that pile on top of each other. The place where you run into difficulty is just, I can create a simple version that's a variant of this. So now let's say that I create something that looks like this, like a funnel. And so anything outside the funnel just gets mapped straight down. But anything that's inside the funnel goes to this one point. And that's not okay because we're creating an atom over here, right? Because now this thing has some finite measure associated with it, and we're taking a region with a finite measure, and we're putting it all onto one atom. So that's a notion, that's just to show you things that work and things that can go wrong. But in general, this is a fairly general thing you can do, and pretty cool. Yeah.
Sorry, can you say again why it doesn't happen?
Why it's okay here? So a line in the 2D space, so if I look at the area of a line, so if I look at mu of the line, it's still going to be 0 because the line has no area. Versus here, this does have area. Again, I'm not doing all the things very formally here, but to give the intuition of why this works. So the next property or theorem that I want to mention, so these 2 things I showed you are for combining processes and stretching and squeezing processes. These are ways to create processes, right, from other processes. So we just talked about 2 ways that you can take an existing Poisson process or multiple processes and adapt it into different ways and still end up with a Poisson process, right? So one way was to slice it or add them, you still end up with a Poisson process. One is to stretch and squeeze and restrict them. So this is technically called a restriction. And you can end up still with a Poisson process. So the next theorem that I want to mention has to do with what if you want to now compute some function based on the Poisson process? You're not just interested in the process itself, but suppose that f pi is equal to some, oh, I just do that up there, right? Let me change this to g. So make sure it's very clear. So g of pi is a sum over all the points in pi. Right, so this is now turning a set of points into a number. So when might this happen? Well, maybe we're interested in the heights of all these trees that we have grown in our forest, the total height, like the sum of all the heights, right? Or the mean of all of them, or sorry, the mean of the sum of all the heights. Or we want to know the total number of buses that have stopped by, right? So then g of x is just 1 and we're just counting. So that's a very simple g of x. A more complicated function might be that, let's say that now this represents like space, and here we are, here is our rocket ship, right? And there are certain planets nearby, or things nearby, and we want to know the gravitational potential here. And the gravitational potential is additive, right? So there's going to be some potential that comes from this dude, and there's going to be some potential that comes from this dude, and some potential from here. They're all going to add up. So this notion of, I want a function, because it can take in as many other parameters, right? You can have any other parameters associated with it. The only restriction is that in terms of x, it has to have. There's a number of interesting functions that might happen to fit that. Okay? still, it's restrictive, but at least it's a start. At least do some interesting things, like out of gravitational potentials. Then the expectation, and notice that this thing is going to be random, right? Pi is, so pi is random, so g is going to be random, right? So this is going to be a random variable. So the expectation of this one is equal to the integral over the entire space, g of x, mu dx. And this may either be bleedingly obvious or super cool, depending on how you, or just boring. But what this is saying is that, why this is interesting, is that maybe initially when you were looking at this Poisson process, you were thinking about, oh, like this is such a complicated object, it's a collection of points, right? So now if I have a function on a collection of points, and now I want the expected value of that function. It seems like I have to think about, well, I could have this configuration of points, or I could have some other configuration of points, and I have to take an expectation over all possible configurations of points. And that seems hard, right? This is why this theorem is non-trivial, like just from the outset, right? Why you might not think this is a trivial problem, because this expectation really ought to, when you start out, is looking at over all the possible instantiations. Now, I'm not going to prove this theorem, but in terms of pictures, why does it turn out this way? Right? Because this is a huge simplification. We've gone from looking at sets of points to just looking at a single point, right? And integrating, like this is the sort of stuff you did like in high school, right? Like you just integrated a function over some space. Like how did that happen? Well, it came again from that key property where we described this kind of grid, right? That when I look at this box, like if I want to take the expected value of this function, I just need to ask every single little box, hey, did you have a point? And if you did have a point inside, well, it should contribute to the total. And if you didn't, then it doesn't contribute. And I can ask each little box individually whether or not it had a point inside. And so what that corresponds to is saying that now we're taking expectations, right? If I'm asking the box whether it had a point or not, that's like taking a sample. If I'm taking expectations, I can say, hey box, what's the probability you have a point inside? And if you have a point inside, then how much will that point contribute? Well, it can contribute g of x. So you can think of g of x as the contribution, and this mu dx is the probability that we end up with a point right there. And because of the Poisson process, it has this independence property. We can go to each piece of this independently, and so we don't need to think about all these different instantiations of points in this sort of way. We can think about this as, let's just check every single location and see whether it had a point there, because we know that the points are independent of each other. So again, one of these things that either is super obvious and is like shrug, or is like, oh, that's kind of cool that we were able to go from something like this, right? By just rethinking how we picture this space. So the last thing that I'm going to talk about is this notion of a product space. So far, I've been drawing this and using words like outer space, or forest, or that sort of thing. That's not typically how these are being used, right? Although you could, I imagine. But this notion of like omega can be a combination. So this isn't really a property. This is just something that I want to know. Combination of spaces. So maybe I have my real space, right? Like my physical space. Let me draw that now as just a one-dimensional line, right? So that's my x space. And then I could have another space attached here that has nothing to do with x, right? It could have something to do with like a popularity of x, or a popularity of the location. So this is something about popularity. And now in this space, so this is called a product space because we're putting together two completely different types of objects, right? They don't necessarily mix in any particular way, but we're saying that any sample from this space, we want to be able to sample a location and assign it a popularity, right? So we want to do two things, like our sample consists of two objects, then we can imagine a product space is the space over all outcomes of those objects. So in this case, again, we have x and popularity. So if we put a Poisson process on here, it's still just x's, right? It's still just x's that we put down on this now new space. But the meaning is somewhat different, or the interpretation allows us to do much richer things. And in particular, now we can convert this, for example, into, if we now I'm going to write down popularity as like the length, like, or some distance. So this might become something that looks like an atomic measure, or some atomic thing that says that not only are these the trees, but these are also the heights of the trees, for example. That's a product space. So in this view, it still looks like a Poisson process. In this view, it looks like, oh, I had to do kind of too complicated for two things. It looks a little more complicated. It looks like I had to select some points, and then I had to put some bars on them, and it looks like two disjoint things that were going on, right? But actually, we can view it again as the same picture as this in this product space. And depending on what sort of intensity function or rate function you put on, you can get all sorts of interesting things happening. For example, I could say that actually in the x space, I think the measure looks something like this, right? That there's some more popular locations in the middle. And I could say, or sorry, more common, like in terms of locations, here are the common locations. And then in terms of popularity, maybe I have something that looks like this, that says that actually there's very few really popular things, and there's a lot of things that are very popular. Very unpopular. So if I'm going to put down an x, I'm most likely to get kind of points here. Let me erase these ones for this new picture. Right? And then I might get some bigger ones here. I probably won't get something that's big and out here, right? But here's how it might look. And again, because this whole thing is now just a Poisson process, here I made them independent of each other, but they don't have to be. I could have put something that says that x's that are around here, now let's draw it kind of like this again, are going to be more popular, and x's that are down here I think are less popular, right? So there's conditional dependencies going on here, right? But in this product space, you're still putting down your x's just like you would for a Poisson process. So you can get these conditional dependencies that show up in this picture that over here still are these independent points down. Okay. So that's kind of cool, and that's where I'm going to leave it because next week you'll be hearing about Dirichlet processes and Indian-Velez processes, and as you can almost kind of see what's going on here, you can imagine that these can be derived in this sort of way. Any questions? No? All right, cool. Enjoy lunch.